Hello students. So today we are going to see NCERT chapter 8, which is aldehyde ketones and carboxylic acid. And today is the theory part 4. So we will cover NCERT section from 8.4 to 8.4.4. This is the disclaimer. So what is the objective of today's lecture? After attending this lecture, you will be able to understand the topics which we are going to cover today. So, today we will describe the chemical reactions of aldehydes and ketones, explain the mechanism of few selected reactions of aldehydes and ketones. Okay, so let's begin with today's lecture. First, I will tell you that the NCERT section which we will cover today. So, we will cover 8.4, which is chemical reactions, 8.4.3, which is oxidation. Then next subsection which we will cover is 8.4.4, which is reaction due to alpha hydrogen. And then we will conclude with summary. So let's start with the topic of oxidation of aldehydes and ketones. So first we will focus on aldehydes. So aldehydes are the compounds that can be easily oxidized. Now if I say the word oxidized, I mean they can gain oxygen or lose hydrogen. So aldehydes, they can be oxidized to form carboxylic acids. Now this transformation requires a strong oxidizing agent which facilitate the addition of oxygen. So we need a strong oxidizing agent. So some common strong oxidizing agents which we use in this process, they include nitric acid, which is HNO3, or potassium permanganate, which is KMNO4, and potassium dichromate, which is K2Cr2O7. Now, mild oxidizing agents, they can also oxidize aldehydes, okay, but they are not as strong as the one which I mentioned before, like HNO3, KMNO4, or K2Cr2O7, but they can also oxidize alcohol. So the mild oxidizing agent which we will discuss is a tolerance reagent. So tolerance reagent is an example of a mild oxidizing agent. Another mild oxidizing agent which we will discuss is Felling's reagent. So like tolerance reagent, it is used to identify aldehydes. Okay, and this often results in a color change that indicates a reaction has occurred. So they are basically used to identify aldehydes. But there are certain exceptions also, which we are going to discuss in upcoming slides. So if you look at this reaction, you will see that this is an aldehyde, which is RCHO. So this aldehyde is oxidized to a carboxylic acid. Carboxylic acid which has COOH. Okay, so the given reaction, it represents aldehyde which is oxidized to carboxylic acid. Now if I give you an example, then see here, this shows a specific reaction which involves aldehyde. So here we have a ethanol. Ethanol is a aldehyde, okay, which has CHO group. And when you write the IUPAC name of an aldehyde, you replace the E of alkane by Al. That is Al. So it is ethanol. When you treat the ethanol with nitric acid, which is HNO3, it undergoes the oxidation. So nitric acid acts as an oxidizing agent. Okay. So this ethanol undergoes oxidation and you get a carboxylic acid, which is ethanoic acid. So in case of carboxylic acid, you replace the E of alkane by OIC. So it is ethanoic acid, which is a carboxylic acid. Now continuing with this, now we will see about ketones. So I hope you all remember what are ketones. So ketones contain a carbonyl group which is bonded to 2 carbon atoms. And as we discussed that ketones, they are generally less reactive than aldehydes when it comes to oxidation. So ketones can be oxidized, but it requires a vigorous conditions. This means that the reaction needs to be more intense compared to other type of oxidation reactions. Okay, so you need vigorous conditions to oxidize ketones. Now, the conditions that are necessary for oxidizing ketones, they include a strong oxidizing agent. So here, a mild oxidizing agent won't work. You need a strong oxidizing agent and you need to apply elevated temperature. Now, why this is so? Because ketones, they are more stable and requires more energy to react. Now, when you do the oxidation of ketones, so the oxidation of ketones, it involves the cleavage of carbon-carbon bond. Okay, so this is important that during the oxidation of ketones, there is a cleavage of carbon-carbon bond. Okay, we will look, when we will discuss it with the help of an example, then it will be more clear. Now, what happens as a result of oxidation process, we get a mixture of carboxylic acids. Okay, so when you oxidize ketone, you get a mixture of carboxylic acids. Now, these acid, or I can say the mixture of carboxylic acids, they have fewer carbon atoms than the original ketone. Now, what does this indicate? This indicates that the carbon chain has been shortened during the reaction. Okay, so you need to remember that when you oxidize carboxylic acid, you get when you oxidize a ketone, you get a mixture of carboxylic acid, and these mixture, they have fewer carbon atom than the original parent ketone. Now, if you look at this particular reaction, things will be more clear. Now, if you look at initial reactant, how many carbon atoms it has? It has 3 carbon atoms and it is a ketone, as we all can see. Now, if you look at this example, when you do the oxidation of ketone, you are getting mixture of carboxylic acids. Now, if you look towards the first one, so first mixture of carboxylic acid, you will get when you will do the cleavage of C1 and C2 bond. Okay, so look at carbon number 1, which is labeled as 1 and 2. So when you will cleave C1 and C2 bond, you will see first one, you will get RCOOH. That is, this will be oxidized to carboxylic acid. And similarly, this one also, which is C double bond O CH2R. This will also be oxidized to carboxylic acid. So this will get COOH. Okay. And now if you will cleave C2 and C3 bond, so this is the mixture of carboxylic acid which you will get. The first one will be RCH2COOH and the second one will be R-COOH. Okay. So then you cleave 1 and 2 bond, you get this first one, and when you cleave 2 and 3 bond, you get this one. Now a question might arise in your mind that which bond we need to cleave. Okay, like for this particular example, you can cleave carbon 1 and carbon 2 bond, or either you can cleave carbon 2 or carbon 3 bond. Now, how will you decide that which bond you need to cleave? Okay, so the question for this particular answer is given by one of the rule. Okay, and this is specifically for ketones. So that rule is called Popov's rule. Okay, now what does this rule says? In case of oxidation of unsymmetrical ketones, so Popov's rule says that when you're oxidizing an unsymmetrical ketone when R and R dash groups will be different, that is an unsymmetrical ketone. So when you will oxidize an unsymmetrical ketone, so what will happen? The carbonyl group, which is C double bond O group, it prefers to remain with the smaller alkyl group. Okay, so you will cleave carbon-carbon bond in such a manner that the carbonyl group, it prefers to remain with the smaller alkyl group. Now see this with the help of an example. So here you have 2,5 dimethyl hexane 3,1. So this is a ketone you have, an unsymmetrical ketone. If you see, both left and right side group are different. So this is an unsymmetrical ketone. So one alkyl group is having only 3 carbons. Okay, if you look at this side, then this alkyl group only has 3 carbons and the other alkyl group is having 4 carbons. Now, as I said, that according to Popov's rule, the carbonyl group will prefer to stay with a smaller alkyl group. Okay, so when you treat it with HNO3, which is a strong oxidizing agent, so which bond will you cleave? Now, can you decide? Remember that carbonyl group will stay with the smaller alkyl group. So if you see towards this ketone, okay, then you will see the right side group which has 3 carbon atoms. That is a smaller alkyl group. So this carbonyl group will prefer to stay with a smaller alkyl group. Okay, so when you will do the oxidation, you will get 2-methyl propanoic acid. Okay, so here you will see that this C double bond OH will stay with this, and this CH3, CH3, and this CH2 will be oxidized to carboxylic acid. That this will be C double bond OH. Okay, so you will get 2 molecules of 2-methyl propanoic acid. If you do the numbering, we will start with this carbonyl carbon. The carbonyl carbon gets the first number, then 2, and then 3. So at second carbon, a methyl group is attached. So it is 2-methyl propanoic acid. Okay, so how you got this 2-methyl propanoic acid? It is by the cleavage of C3 and C4 bond, because the carbonyl group prefer to stay with the smaller alkyl group. So that is why we have cleaved C3 and C4 bond. Okay, and not C2 and C3 bond. Okay, is it clear that how you will decide that which bond to cleave? Just simply follow Popov's rule. Okay, now continuing towards the oxidation of aldehydes and ketones. Now let's look at how we can distinguish between aldehyde, or how I can distinguish aldehydes from ketones using mild oxidizing agent. Okay, we discussed about strong oxidizing agent. Now we will discuss about mild oxidizing agents. Okay, so these agents, they are gentle enough to react with aldehydes but not ketones. As I told you, in ketones, you need harsh conditions. Okay, so you need a strong oxidizing agent. A weak oxidizing agent cannot oxidize ketone. So these agents, they are gentle enough to react with aldehydes but not ketones. And now we will see that first test which we will discuss is Tollens test. Now Tollens test, this uses a special reagent that reacts with aldehydes to produce a silver mirror on the inside of the test tube. Okay, so we will use a special reagent, and this reagent, when it reacts with aldehyde, it produces silver mirror inside the test tube, and this silver mirror is a clear indication of the presence of an aldehyde group. Next test which we will discuss is Felling's test. Now this test involves a solution that changes color when it reacts with aldehyde. So when you will react it with aldehyde, it will change the color. Okay, turning from blue to a brick red precipitate. So that brick red precipitate, or that color change, helps us to identify the presence of aldehydes. Lastly, we have the sodium hypohalite test. This test is also known as haloform reaction. So this reaction is used to identify methyl ketones. So we use it for the identification of methyl ketones, and involves the formation of a haloform. Okay, such as a chloroform, which is a haloform, and which can be detected by a distinct smell. So I just gave you an overview of all the 3 tests. Now one by one we will discuss them in detail. So let's talk on the distinguishing aldehydes from ketones. So Tollens test, which is a classical method used in chemistry to distinguish aldehydes from ketones. So this Tollens test is also known as silver mirror test. Okay, now from where this name comes, silver mirror test? So this name comes from the characteristic appearance that results from the test. Okay, as I told you that inside the beaker it forms a silver mirror. So this characteristic appearance, this results from this test. So this test is primarily used to identify the presence of aldehydes. So aldehydes, they have a unique reaction with Tollens reagent that ketones do not. So tolerance reagent is a freshly prepared ammonical silver nitrate solution. Okay. So what is the solution of tolerance reagent? It is ammonical silver nitrate. You can look at the formula. It is AgNH3 whole twice plus. So this is ammonical silver nitrate solution. So in this test, the aldehydes, they are oxidized to form carboxylate anions. Okay. So we will see the reaction in that we will see that aldehydes, they are oxidized to carboxylate anions. Now to perform this test, the aldehyde is warmed with tolerance reagent. So you need to warm aldehyde with tolerance reagent. Now when the test is positive, a bright silver mirror forms on the inner surface of test tube. This is a visual confirmation of the presence of an aldehyde. So you will see that if aldehyde group is present, so this test will give a positive test and it will be a bright silver mirror that forms on the inner surface of the test tube. Now the silver mirror forms because the silver ions are reduced to silver metal. So this silver mirror is forming because the silver ions, which is Ag+, it is getting reduced to silver metal. Okay. So this reduction, what does this reduction indicate? It is a chemical change where the silver ions gain electrons. Okay. So basically there's a reduction process. Silver metal Ag is produced by the reduction of silver ions, which is Ag+. So now let us look at the reaction which is involved in the tolerance test. So here you can see this reaction. You will see an aldehyde which is RCHO. When you treat this aldehyde with tolerance reagent, that is ammonical silver nitrate solution in the presence of a basic medium. So you will see you will get a carboxylate anion which is RCOO minus, and you will get a silver metal. Okay, so you get a silver metal that precipitates as silver mirror along with the water, and you get ammonia molecules. They are side products. Okay, so you need to remember when you react aldehyde with tolerance reagent, in the presence of basic medium, you get a carboxylate anion and you get a silver metal which precipitate as a silver mirror. So now we will see, we are focusing on the tolerance test. So let us see with the help of an example. So if you see over here, this is ethanol. So ethanol is an aldehyde. Okay. Now when you react ethanol with tolerance reagent, in presence of basic media, you will get a carboxylate anion. That is acetate anion, CH3COO minus. And along with that, you get a silver metal, and water and ammonia comes as a side product. So this is an example of tolerance test. Now, there is one important note that you must remember. Ketones do not react with tolerance reagent. Okay, so this is a key distinction between aldehydes and ketones. Okay, so if aldehyde is present in that compound, so this will give you a positive tolerance test. Okay, and ketones do not react with tolerance reagent. But you need to remember, this is interesting, that some alpha hydroxy ketones, they give a positive tolerance test. I told you that ketones do not give positive tolerance test, but alpha hydroxy ketones, they can give positive tolerance test. So you need to remember it. Okay. Now, if you look over here towards this figure, this will tell you what is alpha hydroxy ketones. So if you'll see the carbon which is adjacent to the carbonyl group is alpha carbon. Okay, we discussed it that the carbon which is adjacent to the carbonyl group is alpha carbon, and at that carbon a hydroxy group is attached. So that is alpha hydroxy ketone. To the alpha carbon a hydroxy OH group is attached. So it is alpha hydroxy ketone. So such kind of alpha hydroxy ketones, they give positive tolerance test. Okay. Now we will see about the Fehling test. Now, Fehling test, which is one of the method used to distinguish aldehyde from ketones. Now, this test is particularly useful in identifying aliphatic aldehydes. Okay, so if you have to identify aliphatic aldehyde, this Fehling test is very useful. So this is used to detect the presence of aliphatic aldehyde. This means it is affected for aldehydes that have a straight or branched chains and not for the aromatic rings. Okay. So in spelling test, we will talk about the aliphatic aldehydes, not about the aromatic aldehydes. Now, Fehling reagent consists of, it is made up of two solutions which is mixed in equal amounts. Now, let us see what are those solutions. So, the first component of Fehling reagent is Fehling solution A, and this Fehling solution A is an aqueous solution of copper sulfate, which is CuSO4. And then we have second component, which is Fehling solution B, which is known as alkaline solution of sodium potassium tartrate. Okay, and this sodium potassium tartrate is also known as Rochelle's salt. So in Fehling's reagent, you have a mixture which consists equal amount of Fehling solution A, which is aqueous copper sulfate, and you have Fehling solution B, which is alkaline sodium potassium tartrate, or we can also call it as Rochelle's salt. And the molecular formula is given, which is highlighted in green. So now what happens in this test? Aldehydes, they're oxidized to form carboxylate anions. This means that the aldehyde group is converted into a carboxylate group. So when an aldehyde is heated with a Fehling's reagent, a chemical reaction occurs. So what happens? This reaction results in the formation of a reddish brown precipitate of cuprous oxide. Okay, so when aldehyde is heated with Fehling's reagent, you will see there is formation of a reddish brown precipitate, and that reddish brown precipitate is of cuprous oxide, which is Cu2O. And this precipitate confirms the presence of an aldehyde. Why? Because ketones do not produce this result. Only in case of aldehyde, you will see this precipitate is formed. And specifically, we are discussing about aliphatic aldehydes. Okay, you need to remember it. So if you look at this particular reaction, you have an aldehyde. When you react it with aqueous copper sulfate in an alkaline medium, this will give you a reddish brown precipitate of cuprous oxide, which is Cu2O, and carboxylate anion. So you will get RCEO minus, and you will get a reddish brown precipitate of cuprous oxide, and water is also released as a side product. So this is the Fehling's test. Now moving on further, so we were discussing about Fehling's test. Now let us see with the help of an example. So this is an ethanol. Ethanol is an aldehyde. When ethanol reacts with aqueous copper sulfate in an alkaline medium, you get a reddish brown precipitate of Cu2O, which is cuprous oxide, and you get a ethanoic acid, which is a carboxylic acid. Okay, and water is also released. This is an example of Fehling's test. Now you need to take one note which is important. Aromatic aldehydes do not respond to this test. Now, Fehling's test is for aldehyde. Yes, it is for aldehyde, but not for aromatic aldehyde. Aromatic aldehyde do not react with a Fehling's test. Okay, so only we will talk in terms of aliphatic aldehydes. Now, ketones do not react with Fehling's reagent. As I told you, toluenes and Fehling's, they are for the aldehyde. But in case of toluene also, we see that alpha hydroxy ketone, they give positive toluene test. And in case of ketone and in case of Fehling test, we see that ketones do not react with Fehling's reagent. But some alpha hydroxy ketones, they can give positive Fehling's reagent. That means that in case of alpha hydroxy ketones, they can give positive test in case of toluene's reagent, and some alpha hydroxy ketones, they can also give positive test in case of Fehling's test. Okay. Now we will discuss the third oxidizing agent, which is sodium hypohalite, or I can say it as haloform reaction. This is used to distinguish the aldehyde from ketones. Now we can see that sodium hypohalite, it has a molecular formula which is NaOX, okay, and X over here can be halite, which can be chlorine, bromine, or iodine. Now we have learned that sodium hypohalite forms when halogen gas such as chlorine, bromine or iodine, it reacts with sodium hydroxide. So when halogen gas and sodium hydroxide, which is NaOH, it reacts, then you get sodium hypohalite, which is NaOX. So sodium hypohalite, it is used to oxidize methyl ketones into sodium salts of carboxylic acid. Okay, look at it carefully, that it is used to oxidize methyl ketones into sodium salts of carboxylic acids. So a methyl ketone, what is a methyl ketone? A methyl ketone is having one methyl group which is directly attached to the carbonyl carbon, and it is represented as CH3 double bond O. So a methyl group will be directly attached to a carbonyl carbon. That is a methyl ketone. Now if you look at this particular example, you will see this is a methyl ketone because CH3 over here is directly attached to a carbonyl carbon. Okay, and when you react it with NaOX, which is sodium hypohalite, you will get a sodium carboxylate. Okay, so I said that it oxidizes methyl ketone into sodium salts of carboxylic acid. So this sodium carboxylate, and you will get a haloform. Okay, which is CHX3. So you will see that haloform reaction where sodium hypohalite is oxidizing methyl ketone into sodium carboxylate along with the haloform as the side product. So here X in this CHX3, it can be chlorine, bromine or iodine. Now sodium carboxylate formed in this reaction contains one carbon atom less than the starting material. Now if you look carefully, students, compare methyl ketone, which is the starting material, and sodium carboxylate. In methyl ketone, you will see there are two carbon atoms. Okay, but if you will see in sodium carboxylate, then sodium carboxylate, it contains one carbon atom less than the starting material. Okay, it is one carbon atom which is less. Now the methyl group which is attached to the carbonyl carbon is converted into haloform. So if you look at the methyl ketone, the CH3 which is attached to the carbonyl carbon, it is converted into a haloform. So this carbon, which is this CH3 which is attached to this carbonyl carbon or this methyl group, it gets converted into haloform. So this CH3 gets converted into CHX3 and you get a sodium carboxylate. Now, among aldehydes, only acetaldehydes undergo the haloform reaction. Okay, so only acetaldehyde, which is aldehyde, it will undergo haloform reaction. Acetaldehyde, if you remember the formula, it is CH3 double bond OH. Now, this acetaldehyde, it contains a methyl group, which is directly attached to a carbonyl carbon. That is why this acetaldehydes, it undergoes the haloform reaction. So certain exceptions which you are seeing, students, you need to remember it. Okay, don't get confused because examiner, they will make you confuse among these options only. So the things should be clear to you, because the reason it contains CH3CO group, that is the methyl group is directly attached to a carbonyl carbon. Now further we will see the reaction. So if you see over here, you have a methyl ketone, okay, and when you react a methyl ketone in the presence of a base which is NaOH, you get ROONA, okay. So this reaction involves a methyl ketone which is reacting with sodium hypohalite and to produce a haloform such as chloroform or iodoform and a carboxylate ion. Okay, and you also get a carboxylate ion, and you'll see that further when this sodium carboxylate, it further get converts into carboxylic acid on hydrolysis. So when you hydrolyze the sodium carboxylate, you will get a carboxylic acid further. Now next we will see the mechanism. Okay, we will see the mechanism of the haloform reaction. So what happens in step 1? So first step involves a base abstracting an acidic hydrogen atom from the methyl group, which forms an enolate ion. So first, if you look at this reaction, you will see that this methyl group, which has an acidic hydrogen, this hydrogen, so a base which is NaOH, it will abstract this acidic hydrogen. And when it will abstract this acidic hydrogen, you will get an enolate ion. Okay, and then this enolate ion, it attacks a halogen molecule, which is X2, giving us a halogen substituted carbonyl product. So this last, if you see this RC double bond or CH2X, this is a halogen substituted carbonyl product. Next, we will see what happens in step 2. So step 1 is repeated 2 more times, which means that the enolate ion continues to react with additional halogen molecules so that all acidic hydrogens will be replaced by halogen atoms. So first you see we replaced one hydrogen with one halogen atom. Now this step 1 will continue until you replace all the acidic hydrogens. Still there are 2 acidic hydrogens left. So this step 1 will continue until and unless you replace all these acidic hydrogens with the halogen molecules. So finally you see that to this carbon 3 halogen molecules get attached. So now there are no acidic hydrogens left. Now further what will happen, another hydroxide ion, okay, that is OH minus from base, it will attack the electrophilic carbonyl carbon and leads to the formation of a tetrahedral intermediate. So OH minus will attack this carbonyl carbon, okay, and you will see this electron density shifts towards the oxygen. Oxygen gets a negative charge and OH gets attached to this carbonyl carbon. So you get a tetrahedral intermediate. Okay, now what will happen in step 3? Step 3, in this step, the tetrahedral intermediate collapse, which will result in the cleavage of carbon-carbon bond between the carbonyl carbon and the trihalomethyl group. So there will be cleavage of C and CX3 bond. And this is followed by a rapid acid-base reaction between the newly formed carboxylic acid and the trihalomethyl anion, which is CX3 minus. Look at this reaction, it will be more clear, okay? So this you get a tetrahedral intermediate. As I told you, first there will be cleavage of CX3 bond, okay? So this negative charge on oxygen comes down and this group leave. So there is a cleavage of the C and C bond, okay? Now what will happen again? There will be acid-base reaction where the carboxylic acid and the trimethyl anion occurs, okay? So this CX3 minus which has left, it will attack on this, it will abstract this hydrogen of the carboxylic acid and this oxygen will get a negative charge and you will get CHX3. And further when you treat it with water, you will get a carboxylic acid. Okay, so this was the mechanism. Now we will see the examples of haloform reaction. First, we will see the chloroform reaction. It is a specific type of haloform reaction. Now, in this reaction, a methyl ketone, it reacts with sodium hypochlorite, which is NaOCl, to produce carboxylate salt, chloroform, which is a colorless compound. So, look at the reaction. This is a methyl ketone, which is CH3, C double bond to R. It reacts with sodium hypochlorite, which is NaOCl. It produces a carboxylate salt, which is RCONa, and a chloroform, which is CHCl3. And this is a colorless compound. Look at an example. You have 3-methyl 3-pentane 2-on. So this is a methyl ketone, that is a CH3 group is directly attached to a carbonyl carbon. So this is a methyl ketone. When it reacts with sodium hypochlorite, which is NaOCl, you will get a corresponding sodium carboxylate and chloroform. So you will see that this methyl group, which is directly attached to the carbonyl carbon, is replaced by ONA. So you get a sodium carboxylate and a chloroform, which is CHCl3. Okay. So the carbon-carbon double bonds remain unaffected. So it is important to note here that this carbon-carbon bond present in the molecule, it remains unaffected by the haloform reaction. So this means that the reaction specifically targets the methyl ketone group without altering the other parts. Okay. So in case of ketones, we saw that there is a carbon-carbon bond that gets affected. Here the carbon-carbon bonds remain unaffected if it is present in the molecule. Okay, so it remains unaffected by the haloform reaction. Now continuing with the example, next we will see a bromoform reaction. In this reaction, a compound with the structure CH3COR, okay, this reacts, this is a methyl ketone, it reacts with sodium hypobromite, okay, which is NaOBr, and you will get RCOONA and a bromoform, which is CHBr3, which is again colorless. Next, we have the iodoform test. In case of iodoform, you have CH3COR, which is again a methyl ketone. When you react with sodium hypoiodide, which is NaOI, you get RCONA and you get the iodoform, which is CHI3. Now, this iodoform is yellow in color. Why? Because of the iodine. So, this is used to identify the presence of CH3CO group or CH3CHOH group in a compound. So, that means that the CH3CHOH group, it can produce it produces CH3CO group upon oxidation. Okay, this means that the secondary alcohol, so this group over here, CH3CHOH, it is a secondary alcohol. It can be converted into methyl ketones, which can be detected using the iodoform test. Okay, is it clear? If you look at this particular reaction, you will see this is a secondary alcohol because the carbon to which your OH group is attached is further connected by 2 carbon atoms. So here it is, there will be another carbon atom. So this is a secondary alcohol, and when secondary alcohol, it oxidizes to give you a methyl ketone group. So a CH3 group is directly bonded to a carbonyl group. Okay, so secondary alcohol produces a methyl ketone group upon oxidation, which is detected by the iodoform test. Is it clear? Now we will move on to the next part and we will see about the acidity of alpha hydrogen. Okay, first let us understand the acidity of alpha hydrogens. Now we all know that the carbonyl group, which is represented as C double bond O, it plays a significant role due to its electron withdrawing nature. Okay, we all know that oxygen is more electronegative, so it has a partial negative charge and the carbon has a partial positive charge. Now this group is influencing the acidity of alpha hydrogens. Now the carbonyl group is highly polar because of the electronegative oxygen atom. This means that the oxygen atom pulls the electrons towards itself, which creates a dipole. Okay. Now, as a result of this polarity, the carbonyl carbon becomes electron deficient. Okay, because oxygen pulls the electron density towards itself, so the carbon of the carbonyl it becomes electron deficient. Okay, so this is depicted by the carbon, which has a partial positive charge, and the oxygen has a partial negative charge. Now we all know this. Now what happens, this electron deficiency at the carbonyl carbon, it causes it to pull the electron density from the adjacent alpha carbon. What is alpha carbon? The carbon which is directly attached to the carbonyl group. That carbon is alpha carbon. So now the carbon of carbonyl group is electron deficient. So it will pull the electron density from the adjacent alpha carbon. Now this action polarizes the carbon hydrogen bond at the alpha position. So the carbon hydrogen bond, that alpha carbon, okay, so this carbon hydrogen bond at alpha position get polarized, making it more susceptible to lose a hydrogen ion. Okay, this is important to understand. So finally, the alpha hydrogen becomes more acidic due to their electron deficiency. Okay, how you determine acidity? Which easily donates its H plus ions. So the alpha hydrogen becomes more acidic, and this increases the density and makes the removal of hydrogen more easier. Okay, so that is why the alpha carbon, their hydrogen is more acidic. Now, if you look at this particular example, students, things will be more clear. Okay, if you see this carbonyl carbon, the carbon which is next to this carbonyl carbon is alpha carbon, which is denoted in green color. So this is alpha carbon. Okay, now we can see this alpha, this hydrogen of this alpha carbon, it is acidic. Okay, because this carbonyl carbon, which is electron deficient, it will withdraw the electron density from this carbon. Okay, that is from this alpha carbon, which will make this carbon hydrogen bond more polar. So this alpha, the hydrogen which is attached to the alpha carbon is quite acidic. So now base will come and abstract this hydrogen. So you will see a resonance stabilized enolate ion. So when base will take up this hydrogen, so this carbon gets a negative charge. Okay, and we can see that alpha hydrogen, after donating its shared electrons to the carbon, detached with the base, and then the charge delocalization will occur between the alpha carbon and the oxygen atom of the carbonyl group. Okay, so there will be a resonance, or I can say there will be a charge delocalization between this alpha carbon and the oxygen atom of the carbonyl group, which causes the stabilization of the enolate via the resonance. So the C minus goes here and this electron density goes on this oxygen. So oxygen becomes negative charge and there is a double bond between carbon-carbon. So this enolate ion which is formed is stabilized by this resonance. Now these concepts, students, they are very important because they will build your basics of organic chemistry. Okay, so you need to understand it carefully, that why this hydrogen is more acidic, how this enolate ion is getting stabilized. Okay, so pay attention and listen everything carefully. Now, the removal of acidic alpha hydrogen is done by a base, and this is the first step in forming the enolate ion. Now, removing the alpha hydrogen forms a negatively charged enolate ion, which is the conjugate base of original compound. If this is the original compound, students, then what is a conjugate base? Which this will, when it will donate its H plus, so this acid, when it will donate the H plus, it will form a conjugate base. Okay, so this negatively charged enolate ion is the conjugate base of this original compound. Now, the negative charge on the enolate ion, they can delocalize between the alpha carbon and the oxygen atom of the carbonyl group. So, there is delocalization of this negative charge between the alpha carbon and oxygen atom of carbonyl group. Now, this delocalization, it increases the stability of the conjugate base or of the enolate ion. Okay, so finally we concluded that the increased stability of the conjugate base leads to an increase in the acidity of alpha hydrogens. This is why these hydrogens are more acidic compared to other hydrogens in the molecules. Okay, I hope this is clear to you all. Now we will see the reaction that occurs due to alpha hydrogen in aldehydes and ketones. So the acidic nature of alpha hydrogen, it allows aldehydes and ketones to participate in specific reactions. Okay, so aldehydes and ketones, they undergo reaction due to the acidic nature of alpha hydrogen atoms. Now this acidity is crucial for the reactivity of these compounds. So we all know that aldehydes and ketones, they undergo following reactions because of the acidic nature of alpha hydrogen. So the first reaction which we will discuss is aldol condensation. Now this reaction involves the formation of carbon-carbon double bond between two aldehyde or ketone molecules. Next, we will discuss cross-aldol reaction. This is similar to aldol condensation, but it involves two different aldehydes or ketones. In aldol, there is same aldehydes or ketones, but in cross-aldol, it involves two different aldehydes or ketone molecules. So first, we will start looking at aldol condensation. Okay, so these reactions are important. Aldol and cross-aldol. You should know what is happening in this reaction and what is the mechanism of these reactions. So for an aldol condensation to occur, the most primary important thing is that the aldehydes or ketones that are involved, they must have at least one alpha hydrogen. So alpha hydrogen is important. Okay, so this is hydrogen atom that is attached to the carbon next to the carbonyl group. Okay, so the reaction takes place in the presence of a dilute alkali which acts as a catalyst. Okay, so there will be a dilute alkali and this will act as a catalyst. Now, what are catalysts? These are the substances that speed up the chemical reactions without being consumed. Now, let us look at the aldol reaction. So this reaction is known for forming beta hydroxyaldehydes. Okay, so this is important. This when this reaction happens, you get beta hydroxyaldehydes, which are also referred to as aldol. That is, on beta carbon there will be a OH group attached. Okay, and this is also referred to as aldol. Now look at the example. There is ethanol, which is an aldehyde. When you treat it with a dilute alkali, which acts as a catalyst, you get an aldol product. That is 3-hydroxybutanol. If you see that this carbon, which is directly attached to this carbonyl, is alpha carbon, and next to alpha carbon is a beta carbon. So on the beta carbon, there is OH, which is hydroxy group is present. So that is why we call it forms beta hydroxyaldehydes, or it is also called as aldol. Okay, we will look at the mechanism, so you will get to know how this reaction is happening. Now look at this mechanism. One by one, we will break this into steps, which will help you understand more clearly. Step 1 is the formation of the enolate ion from one equivalent of an aldehyde. So you have initially aldehyde, we will form an enolate ion. Okay, so here the aldehyde, it loses a hydrogen ion, forming a negatively charged enolate ion. Now we know that this aldehyde, in this aldehyde, there is a methyl group, which is CH3 group, and that hydrogen of that methyl group is quite acidic. Okay, so this base will abstract that proton and you will get an enolate ion. So if you see over here, this oxygen has a negative charge there, and there is this double bond. So this is an enolate ion, and this ion is highly reactive. Okay, so this is the step 1, which is the formation of enolate ion from one equivalent of aldehyde. Now what happens in step 2? The enolate ion attacks another equivalent of aldehyde or unenolized aldehyde. So now you have a enolate ion. Now that enolate ion, I said, it's quite reactive. Okay, so now it will attack the another molecule of a aldehyde. Okay, now when it will attack other molecule of aldehyde, this will result in the formation of a new compound, which is called aldol. And here it is 3-hydroxybutanol, which is formed after the removal of hydroxy ion. So if you look over here, this is your enolate ion. It attacks another molecule of aldehyde or unenolized ion. Okay, so this negative charge on oxygen goes down, and there is carbon oxygen double bond. And if you see further, you get this intermediate. Okay, and then this O minus abstracts one proton and you get an aldol product. Okay, so there's a removal of hydroxy ion, which is OH minus ion. So if you again see at beta position, OH group is attached. So you will get the product as 3-hydroxybutanol. So product is an aldehyde, ALD, with a hydroxy OL group. That is why it is called aldol. AL stands for an aldehyde and OL stands for the hydroxy group. That is why it is called aldol. So I hope this mechanism is clear to you, students. Now forms beta hydroxy ketones, which is called ketone from ketones. Earlier we were forming beta hydroxy aldehydes, which was called aldol. And similarly, we will form beta hydroxy ketones, which are called ketone. So if we look at the example, so we have a propanone, which is an ketone. Okay, when you treat it with barium hydroxide, which is BaOH2, it forms a ketone. Okay, and that ketone is 4-hydroxy 4-methyl pentane 2 on. Okay, if you see that on 4th carbon, a hydroxy group is attached and a methyl group is attached. So you will get a ketone. Okay, and the mechanism will be similar as we have studied in the case of aldehydes. Okay, is it clear? So continuing with the aldol condensation, let us look at the mechanism with the ketones. So if acetone, which is a ketone, so step 1 will happen. It will form an enolate ion with one equivalent of ketone. Okay, so this is an enolate ion which is formed base, which is OH minus, abstracts the acidic hydrogen and to get a corresponding enolate ion. So a ketone loses a hydrogen, forming a negatively charged enolate ion. And again, same step will happen, that enolate ion will attack another equivalent of ketone to form a ketone. Okay, so this is similar as we have studied in the case of aldehyde. So this results in the formation of a compound which is known as ketone. And here it is 4-hydroxy 4-methyl pentane 2-on, because at 4 carbon a hydroxy and a methyl group is attached. Okay, try this mechanism once with yourself, students. Things will be more clear to you. So this steps highlights the nucleophilic nature of the enolate ion. Now this enolate ion, in which oxygen has a negative charge, it will act as a nucleophile and it adds to the carbonyl group of second ketone molecule. This is the second molecule of ketone, and it will attack this carbonyl group of the second ketone molecule. So product is ketone with the hydroxy OL group. So it is ketone. Ket comes from ketone and OL comes from hydroxy group. So the final name is ketone. Okay, so this is the mechanism. Once just try it by yourself and you will get the product. So continuing with it. So now we will see that aldehydes or ketones readily loses a water molecule of water upon heating. So this, when aldehydes and ketones, when they are heated, they readily loses a water molecule, and this dehydration process leads to the formation of alpha beta unsaturated carbonyl compounds. So dehydration is the removal of water. When water is removed, you get alpha beta unsaturated carbonyl compound, and these are the final products of aldol condensation, which is characterized by the double bond between the alpha and the beta carbon. Okay, so there will be double bond between the alpha and the beta carbon. So example of dehydration, if you look at this particular reaction, this is the aldol product which we have got, that is on beta carbon a OH group is, hydroxy group is attached. When a dehydration process occurs, that is removal of water, so you will you will get a aldol condensation product. There will be a double bond between alpha and a beta carbon. Alpha carbon is the carbon next to the carbonyl group, and adjacent to alpha carbon there is beta carbon. So you will get a double bond between alpha and beta carbon. Okay, so you will get but2-enol, and this is the final product. Okay, so if we look at the mechanism, students, so base, it abstracts the acidic proton forming enolate ion, which is followed by the loss of OH minus ions. So look at this. If we say that on this carbon which is adjacent to a carbonyl carbon, it has acidic hydrogen. So base will abstract this acidic hydrogen, okay, and you will see this is the enolization step. The enolate ion will form, and finally there will be loss of OH minus ions, and you will get a dehydration product which is but2-enol. Okay. Now we will see this dehydration of ketone. Similar to aldehyde, there is of ketone also. Okay, so this is a ketone product. When water is removed, there will be a double bond between alpha and beta carbon. So this is 4-methyl pent 3-ene 2-on. Similar is the case for ketone also. Okay, so if you look at the mechanism, it will be similar, that the base, it will abstract the acidic proton, which will form an enolate ion, and which is followed by the loss of hydroxide ion. Okay, so if you look over it, similar it is happening. This base will abstract this hydrogen. Okay, you will get that enolate, and when you get that enolate, you will see there is a loss of OH minus ion, and you finally get alpha beta. You will get a double bond between alpha and beta carbon. So this is a dehydration product. Okay, so generally the name aldol condensation applies to the reactions of ketones also. Reason, because of similarity with the aldehydes. Now we will see about the cross aldol reaction. Now cross aldol reaction occurs when when there are different aldehydes or ketones. In earlier reaction we saw that there is same aldehydes and ketone. When there are different aldehydes or ketones, you say this is cross aldol. So one of the reactants must contain alpha hydrogen. Okay, so it is important that one of the reactant should contain an alpha hydrogen. Now this reaction is carried out using an alkali as a catalyst, and it requires heating. So this alkali helps to deprotonate the alpha hydrogen, facilitating the formation of enolate ion. If you look at example, this is a benzaldehyde, which is an aldehyde, and you have acetophenol, which is a ketone. Now this ketone has an alpha hydrogen. Okay, when you treat it in a basic medium, when you treat it using an alkali, you see you get a major product. Okay, that is, there is double bond between alpha and beta carbon. So this is the final product which you get. So if we continue with cross aldol condensation, now both the reactants containing alpha hydrogen atoms. Earlier we saw if one of the reactant is containing alpha hydrogen. Now if both of the reactant contains alpha hydrogen, you get a mixture of multiple products. Okay, each carbonyl carbon can act as both nucleophile and electrophile. So the one which is enolate will act as a nucleophile which will attack on the electrophile, which is the carbonyl carbon or unenolized one. Okay, so this reaction now lacks selectivity. This means both reactants can act in multiple roles. So the reaction can produce a variety of different products. If you look at this reaction, you have a ethanol, which is CH3CHO, and you have a propanol. Okay, so when you will do the cross aldol reaction, you will see that there are both aldehydes. They can react with each other in different ways because due to their alpha hydrogen. In ethanol also there is alpha hydrogen, and propanol also there is alpha hydrogen. So this will give you a mixture of products. First, they can do it can give self aldol products, and it can also give cross aldol products. So this will give you a mixture of products. So both aldehydes have alpha hydrogens. So this will result in 4 aldol products. Okay, so this illustrates that the complexity and lack of selectivity in cross aldol condensation. So if we continue, we will see first we will get 2 self aldol products. Okay, first one is but-2-enol and next one is 2-methyl pent-2-enol. Okay, that is but-2-enol is formed when the reaction is between 2 ethanol molecules. So this is self-aldol product. Okay, and when 2-methyl pentane-2-ol is formed when there will be self-aldol between propanol. So these are self-aldol products. Okay, the mechanism is same. You can try it by yourself. So this is the product of between 2 molecules of ethanol, and this is the self-aldol product of between 2 molecules of propanol. So these are the 2 self-aldol products, and next we will see cross-aldol products. So you will get 2 cross-aldol products. Okay, so propanol is enolized and ethanol acts as electrophile. So propanol will be enolized, which will act as a nucleophile, and it will attack on ethanol, which acts as an electrophile. So you will get 2-methyl but-2-enol. And when ethanol is enolized and propanol acts as electrophile. Second one, when ethanol will be enolized, acts as a nucleophile, and it will attack the propanol, which acts as an electrophile. So you get 4 products, 2 self-aldol products and 2 cross-aldol products. Okay, so cross-aldol condensations become challenging to control for specific product formation. Okay, so I hope it is clear, self-aldol and cross-aldol also. So first we saw the oxidation of aldehydes and ketones. It can easily oxidize to carboxylic acids. Ketone requires harsh conditions. Then we saw Popov's rule, okay, which we saw in unsymmetrical ketones. Then we saw the test. We discussed about tolerance test, which gives silver mirror. We discussed about Fehling test, which gives red-brown Cu2O precipitate. And we saw the iodoform test, which gives yellow precipitate with methyl ketones. Then we talked about alpha hydrogen. They are acidic due to the adjacent C double bond group. And it forms a stabilized enolate ion, which leads to aldol and cross-aldol condensation. In aldol condensation, it forms beta hydroxyaldehydes, which is also called as aldols, or ketones, which is called as ketones. It requires alpha hydrogen and a basic catalyst. The products, they can dehydrate to form alpha beta unsaturated carbonyl compounds, so that when you remove the water, it will form alpha beta unsaturated carbonyl compounds. Similarly, we talked about cross-aldol reaction. It occurs between different aldehydes or ketones. One reactant must have alpha hydrogen, and multiple products form if both have alpha hydrogen. Okay, so it is challenging to control the selectivity. So I hope, student, today's topic is clear for you. Thank you for your attention. Please try the mechanism by yourself. Things will be more clear. I hope you all have a good day. Thank you.